So today you're going to get to experience one of my beautiful drawings, and I ask that you just bear with me a little bit because normally I do these on paper and today I'm doing it on a computer, so they might not be as beautiful, but we'll do what we can. So I'm going to talk a little bit about channel proteins and how we exchange sodium and potassium. So first, what we need to do is draw a cell. So this is the cell. This is the cell membrane here, so anything inside of the circle is going to be intracellular. Anything outside of the circular is going to be extracellular. So along the cell membrane, we have a bunch of little channels. They're like little holes in the membrane. And these allow for the exchange of nutrients and waste. Importantly, for our purposes, these allow the exchange of sodium and potassium. We have two really important ions to think about. If we remember, the ion that's found in high concentration inside the cell is potassium, and we abbreviate that K+. And there's a tiny bit of sodium, and we abbreviate that Na+. On the outside of the cell, we have a lot of sodium, Na+, and we have a little bit of potassium, K+. So the different types of channel proteins that we have determine the effect that they're going to do. The first type that we have are going to be called ligand-gated channels. So ligand-gated channels open and close in response to the binding of a ligand, which in the case of neurons is going to be a neurotransmitter. So these open and close in response to binding of neurotransmitter/ligand. The other type that we have are called voltage-gated channels. These open and close in response to changes in electricity, which is changes of sodium and potassium. The other type that we have are called mechanically gated channels, and these open and close in response to physical stretch. So what happens, for example, a purple neurotransmitter here will come and it will bind to this ligand-gated channel. The ligand-gated channel will open, and so there will be a little hole in the membrane, and that will allow sodium and potassium to exchange. So if there's a ton of potassium inside of the cell and very little outside the cell, the potassium is going to exit because it wants to have the same number of ions inside the cell as it does outside the cell. The opposite is true. So sodium, there's a lot of sodium outside of the cell, not a lot inside the cell. So when there's a hole available, sodium is going to want to rush in to equalize. Okay. So what happened, number one, neurotransmitter in purple binds to the ligand-gated channel. Number two, ligand-gated channel opens. Number three, K, potassium, exits the cell, and sodium, Na, enters the cell. So their goal, the exchange of sodium and potassium, is just to balance it out. So there's the same number of sodium inside and outside, same number of potassium inside the outside. The example I like to use for this is like if we're in a tiny room and there's 200 of us and we open the door, as many people as possible are going to leave because they're all jammed into this tiny room. So they want to equalize, so there's 100 people inside, 100 people outside. So same kind of thing happens here with sodium and potassium. So the goal is to equalize. Okay, so there are a few other holes and proteins within the cell membrane. So for example, there are little channels present all the time that we call leak channels. So these little ones in blue, these are leak channels. These are open always, but only allow a small amount of exchange. The other type that's really, really important, I'm going to do here in green, whoops, in green here, we have other pumps called the sodium potassium ATP ACE pump, and this is probably a review for a lot of you. So sodium potassium ATP ACE pump. So this utilizes ATP, which is energy, to pump sodium and potassium against their concentration gradients. So here we are exchanging sodium and potassium against their gradients, and we use ATP to do this. Sodium potassium ATP ACE pumps are always working. Leak channels are also always working. The ligand-gated, voltage-gated, and mechanically gated channel proteins only open and close when one of their situations is met. They're not open and closed just randomly. They have certain things that cause them to open and close.